there are a lot of different ways to find the slope of a line. In this video, I wanted to run through a lot of those. And like I've said in a lot of previous videos, sometimes students ask me, well, should I solve it this way? Or, I mean, it doesn't really matter to me how you solve it. It just matters that we have a way of solving it. And having more than one different way that we understand it is actually really valuable, because sometimes one way might be a lot easier than another. Or, sometimes we might get stuck with one process. It's nice to have a different to fall back on in the case that we do get tripped up. But let's return back to slope. I've already kind of covered out a little bit, but I wanted to start off with certain formulas for slope based on how it's defined. So m is the variable we often use for slope, as I mentioned before, and it's often defined in a few different ways. First being rise over run, which is a very graphical, visual way of determining slope by determining, well, between one point to the next, how much did it go up and how much did it go sideways, right? Because rise is a very vertical change, run is a very horizontal change. But mathematically, we could also define it instead of that. That's kind of more conceptually. Mathematically, we often refer to it as delta y divided by delta x, where this is a mathematical formula for change in y, which is just a way of saying, well, from this point to this point, what was the change? Same with change in x, is what we call delta x. And in calculus, there's something what we call dy over dx, which is a very similar idea, but it's called a differential. It's a little bit more complicated, but it comes down to the same ideation of what's the ratio between the change in those values. And basically what we're doing is we're creating a multiplicative number, the slope, which will multiply into x, which corrects for the slope. And in taking a ratio, that's the whole purpose of the division, is that when we divide into that, then when we multiply into x, it will make sure it all works properly. And we'll try to look at that as we do math. Sorry if that was a little bit too spacey. But anyways, the formula for delta y and delta x, mathematically, it's always the difference between the two numbers, right? Because if you want to know, well, between these 2 points, how much did it rise or how much did it run, you would take the difference between the coordinate points. Like say x is at 2 here and 5 here. Well, those would obviously be 3 apart. And the way to find that is by subtracting them. So like if we want to know how much did it rise, well, what's the difference between the two positions? What were their locations, and subtract. Same with delta x. And so let's use these ideas to return back to our previous examples just to try to look at the slope of what those will be. And also just to mention on the note page and in my slides here, I've kind of identified what does slope mean, but we'll kind of look at that as we go over some of the examples. So let's say we return to the graphs from some of the previous videos, like y is equal to 3x minus 4. Well, we already know the slope is 3. We already talked about that and why that's true, because when it's in slope-intercept form, you can read the slope directly. That's one of the benefits of using this format for a linear equation. But let's try to use those other ways. Like, well, we already talked about rise over run, which is just if you take 2 of the points and you find the if you make a little triangle, you can see, well, how much did it go up and how much did it go over? But let's say we were going to use the delta y delta x formula, because again, we could use those formulas to find slope, which is probably a way a lot of you like to use, because if I'm stuck, I'm not really sure what to do, it's nice to have a formula to go to where I don't have to do much thinking, but I can kind of just plug stuff in and figure it out that way. But what I want to make sure that the formulas make sense, because that's the whole point, right? If I use a formula and I solve something, that's great, and I can get the answer, but what's really the point of doing it that way if I don't really get the formula? And that is kind of why I'm diving into it right now. But basically, if I choose, and also you can choose any points you want for your x1, y1, x2, y2, but what is important is that x1, y1 is a single point and that they're in the same place in the formula, and same with x2, y2. Usually we pick points from left to right. We could use the same points we picked from before, but we already kind of know, well, if I pick those points, what will the rise and the run be? But let's just pick 2 different points just for the sake of why not. But let's say we're going to use these other 2 points, which were -1, -7, and 2, 3. So I'm just sort of picking random points from my t-table over here. And again, you can pick whatever points you want. Oops, let me use the same color. This one and this one. And so this will be my x1, y1, and this will be my x2, y2. And you know, whether we, and this is something I don't know if you're wondering, why do I write it like as a coordinate sometimes in parentheses, and why do I write it like this in other times? Well, the coordinate form, and this can be confusing because this looks exactly like when we were talking about interval notation, you know, in previous sections. What this means if I'm talking about an interval is all the numbers in between these 2 points. So what I'm trying to say here is it's very contextual. This could mean all numbers in between, but it could also mean an ordered pair, left 3, up 14/3. And it's really just a context. Are you talking about a set of numbers, or are you talking about a coordinate on a grid? And so in math, we often reuse symbols and we reuse notation. It's really annoying, even for me, because I have to explain the differences between these. But basically, it should be pretty obvious when it's one or the other. And if you're never sure, you can always ask. But, you know, we write things in a lot of different ways. A lot of times we don't talk about why, but it's just sort of a result of ancient notation. These are just ways people wrote it. And these are the ones that have stuck around for the longest. And so we're sort of slaves to the common way of writing it. There are other ways we can write it, right? But it's all about what's easiest. And it just happens that these are both kind of easy representations. I do wish that it did not look the same, though, if you catch my drift. But anyways, let's actually plug those in. So we have x1 is -2, y1 is -10. And x2 is 2, y2 is 2. Basically just using those 2 points in yellow. And then plugging that in to my formula, slope formula. Or again, what you could do is you could just say, well, what's the rise and what's the run by building a kind of a larger triangle. But the farther apart they are, or say that they're not right on grid points, it'll be a little bit harder. That's where the formula comes in handy. So y2 is 2, y1 is -10. Also be careful when you're using the formula that if you are to plug in a negative value, that if you're subtracting a negative, remember that makes a positive. So basically use parentheses when you plug negatives into formulas and functions and all sorts. Basically anywhere in math, when you plug in negatives, be careful, make sure you use parentheses to make sure that we're applying the negative to whatever other math is going on. And then if we have x2, that was 2, and x1 was -1. Again, sorry, I scrolled away from my table, but basically using all those values. Oh, it looks like right here I'm using the point -1, -7. So I'm using the wrong point, sorry. And again, it doesn't matter which point you use, just make sure you're using the same point. And it looks like I just messed it up. So let's just use this one because I marked it on the table, which is not correct to the one I marked in the graph. So excuse my little error there, but let's just use -2, -10. So this should be really -2. But I think I might have said this, but if I didn't, it doesn't matter which points I choose, it will be the same answer regardless. And the reason why is because, well, no matter which points I choose, they're all on the same line. They're all going to have the same slope because it's always going to be the same ratio regardless of if it's a big triangle or a small triangle. But what I would end up with is 2 minus a -10, which is 2 plus 10, over 2 minus -2, which is 2 plus 2, which is, of course, 12 over 4, which would yield 3 upon simplification. But the point stands. No matter what ratio I take there, it's going to have the same, the ratio will always simplify to the same 3 because the slope of this line is 3. And every line has its own unique slope. And say when we're looking at the next line down here, we didn't find the slope yet of this one, and it's not obvious what the slope is from the equation of the line, which was right here. But basically, anytime you have any 2 points, we could use these 2 points to find the slope by using the slope formula. So if we did that here, we'd have m is equal to, well, let's just call this point 1 and point 2. We'd have y2 is 0. And notice that the intercepts are really nice because there's some zeros. 0 is the easiest number to work with. And then minus y1 would be minus negative 3. And then we'd have over x2, which is 1.5, minus x1, which is 0. So that's about the easiest math I can probably do, which is double negative 3 is positive, and 1.5 minus 0 is 1.5. And then 3 divided by 3/2, this should just be 2. And simplifying that, even if there are decimals or weird numbers in those locations, it still will simplify. You could write, and the slope often is represented as a fraction. You could simplify it into a single number. You could leave it as a fraction. Again, it doesn't really matter how you answer it, but it's often better to leave it as a fraction, or really write it as simple as you possibly can, just for a better grasp of what that number means. And also what this means is those points were kind of weird, but if I started with the y-intercept, which was 0, minus 3, since the slope is 2, what that means is as I'm going up and to the right, sorry, my image is mirrored there, up and to the right on the graph, it's going to have a rise of 2 and a run of 1. Because while it's just 2, you could always think of that as a ratio of 2 to 1, which is an equivalent ratio to 3 to 1.5. But basically, as I move along this line, if I were to rise 2, that implies that should run 1. So that would give me another point, well, 1, negative 1 would be another point on the line. And I could then rise 2 more and run 1. But you could find more points from the slope. And notice that those would still be on the line. And it would maintain its patterns. And the slope just tells us something else about the line. It tells us, well, what is that respective rise of a run. And lastly, when you do have a line in standard form, you can always find the slope by taking, well, there was a formula on the previous page, which was negative a over b, which is just the ratio of this number to this number. In the next video, we'll talk more about that and how what we often say is solving an equation or solving for y, which is a common thing we do in algebra just to rewrite our equation in slope-intercept form.